thought it would be nice to kick off a conference about big data by talking about data science, which is, I think, in a way, the reason we care about big data. As Ruben said, I'm from Cloudera. I think most of you will know Cloudera from our distribution of Apache Hadoop, but CDH is a bit more than Hadoop. We do search, we do interactive query through Impala, which Oscar mentioned, and we also do data science and machine learning, whatever that means. Maybe I can talk a little bit about what I think that means and what we do in this area at Cloudera and why you may care. So I'd like to start off with a slide that I think everyone starts off with in presentations like these, which is, what is big data? It's almost concerning to me that we keep asking this question. What is it? Why do we care? Why are we here? What's the big deal about big data? So I also found a word cloud online to try and answer the question. And it looks like big data is about big data and business, scientists, people, skills. It has something to do with these things. It seems to be what people talk about when they talk about big data. But I mean, even at Cloudera, when we talk about today what people are using it for, it's not those things, and it's almost not as exciting yet. And this is a diagram from even one of our blog posts on our website describing using Apache Hadoop to do ETL, extract, transform, load jobs over data. This is something a bunch of companies need to do. You need to ingest data, put it into a schema of some kind, and do this at large scale, and then maybe later query it. And this is important. I mean, don't get me wrong. Everyone has this problem. But somehow this is not what we dream about when we dream about what big data means and why it's new and exciting and different. This is just moving bytes around, really, copying data, transforming data. So when I think of what it is we dream about when we dream about big data, it feels more like it's things we think of as data science and machine learning. New results, not just pushing data around for fewer dollars. So for example, here's an example of something we did at Cloudera 2 years ago. Took data from the FDA, which is the Food and Drug Administration in the US. Data over reports of negative interactions with drugs, so patients that took a drug and had some adverse reaction to it. And from that you can figure out what drugs seem to cause adverse reactions, but sometimes the reactions are caused by interactions of 2 drugs or 3. And that's not as obvious from the data. To find these sorts of events, we have to look at all pairs or all even triples of drugs and analyze whether they seem to correlate with negative interactions. Now this was just a bit of a toy project, but it turns out we actually found a couple apparently new negative drug interactions that weren't apparently cited in the literature. Maybe they're important, maybe they're not. But this seems important. This seems more interesting than just copying bytes around or transforming data. This could impact somebody's life. And again, this is just a toy example, but this is the sort of stuff that I think interests me, and I imagine interests you guys when you think about big data and what the promise is and why this is new and interesting. So to me, in the value of big data, you could view and the technologies we're seeing today is that it's moving this curve of cost versus value. So as we spend more and more money, we can accomplish more and more complicated and maybe useful data projects, right? And at some point, the marginal value just doesn't make any sense. We can spend a certain amount of money with old technologies and just never really get to some of these projects and types of business value that we could imagine in our minds. So new technologies and new approaches are just simply moving this curve up and to the left. And you can think of it 2 ways. On the one hand, you can think of it as pushing the curve left and making existing projects cheaper. But I like to think of it as pushing the curve up, making, for a given amount of feasible expenditure of time and effort and money, making new things possible. And in fact, it should be making things possible that aren't just better quantitatively, but different qualitatively. New kinds of projects that we might have thought of before but couldn't implement, like this, like drug analysis. And I'm sure if I asked any of you, you could come up with a big data dream that you have that might be feasible now that we have the technology. So think of big data as opening up not just slightly cheaper ETL or slightly faster data processing, but entirely new things to do with data. So I mean, if that's the case, if there's all these things we could be doing with data and these technologies are unlocking those things, why haven't we done them already? What's so hard? What's the barrier between having the technology in our databases and this magical land of big data dreams? There's still a gap here somehow. And the gap is something we have to figure out how to cross. This is how I think of the gap. On one hand, I think we're already pretty good at collecting data, storing data, and by good I mean it's cheap and it's easy and it's accessible. We're even good at modeling the data, querying the data, understanding the schema of the data. This is well understood. I think all of us in this room are fairly familiar with this, even at large scale now. Things like HDFS and Hadoop make this pretty straightforward. And again, I think we can dream on the other side of how we would deploy the analysis and the insights we'd get from this data. But it's not clear how we get from here to there. What's in the middle here? If, let's say I've got a database of all my users' activities over the past 10 years. You think I could target my marketing at them better. You'd think I could personalize my site and send them new recommendations every day that they'll love. And you could in theory, but it's not clear how we cross that gap, right? I mean, how would you begin? Is there a button you push? Is there a server you run that just magically finds recommendations and finds insights? There isn't really, and that's a shame because we've got all these nice servers and tools and toys for the data collection, the ingest, and the transformation. So we've got to cross this gap. We've got to find a way to more reliably, repeatably, efficiently cross this gap for not just one problem, but 10 or 100 problems within our business. It has to be just that easy. It has to be as easy as setting up a database. And it has to be something that can run continuously and continue to build and learn from new data. It needs to be something that's not just a manual process that highly paid PhDs execute once a month. It needs to be happening continuously every second. I like to call this talk about this as an analogy to a lab and a factory. I think we all, as an industry, understand how to do this in the abstract. We know what we want to do. We even, in the abstract, know some of the techniques we could use to apply to data to do the learning, but somehow we haven't productionized it. We're not good at mass producing this learning, mass producing learning systems. We're not good at just pressing a button and analyzing our data and having a runtime system in the way that we're used to databases just working out of the box. So there's this gap between knowing how to do it and productionizing it. Now, this is where I think data science comes in. Whatever it means, I think it means this. It's whatever we do to cross the gap between having data and actually implementing a runtime learning system on top of that data that can be fed back into a business, doing that repeatably, reliably, quickly, and efficiently. So obviously we can do that today. In a sense, it's just difficult. And whatever it is we call that data science. And the people that do it are called data scientists, right? And our job as data scientists is to make this easier, to make it cheaper and more accessible to do whatever this data science thing is, so that we don't have to have a bunch of data scientists. So what is a data scientist? My colleague in the US describes a data scientist as a person who is better at statistics than any software engineer and better at engineering than any statistician. And I think that's true. Somehow the data scientist role, the thing that bridges the gap, involves necessarily math, applied math, statistics, but also engineering. But it's not just ideas in the lab, it's the implementation of those ideas. And to cross the gap, we have to have both. And these are actually fairly different worlds. I think it's one thing to be an engineer and go from a relational database to a NoSQL database. In the scheme of things, these are fairly similar things. They're servers, they have tuning, they have latency, et cetera. But moving to building a learning system is actually quite a bigger jump. And likewise, if you started out in the applied math world and you're a statistician, the world of databases is actually fairly far away compared to statistics versus machine learning. So there is this gap between the two, and data science is somehow what's in the middle, and we don't have enough of it today. And we can either make more data scientists or we can make data science easier. And I like the latter. Now, I'll throw one rough anecdote at you. I mean, if you believe that 5 to 10 years ago we had statisticians and we had engineers and we didn't have many people in the middle, well, people are coming into the middle from both sides. And I find it's mostly actually the engineers out there who are picking up the stats and the math versus the statisticians picking up the engineering. So if you're an engineer in the room, and I actually imagine most of you are, you're in good, if you want to be a data scientist, I think you're in a good place. I think it's actually easier to acquire the math and the stats than the other way around. Most of the problem is actually in the building of the systems, not the conceiving of the math. So this is one trend I'm seeing. Data scientists are coming in from the engineering side of the house rather than the stats side. But why is this a new problem? I mean, honestly, data isn't new. Big data is not even new, right? I mean, we've always had probably a bit more data than we could comfortably deal with, right? And we've had statistics in the past. I mean, this isn't new. People have been doing statistics for over 100 years. So why is this a new problem all of a sudden? So let me speak to why I think this is actually a slightly new problem in the last 5 years. And historically, this is how I would describe the data science problem, which is classically called statistics or data analysis. Input is smallish, fits on one machine. This is the world of classical statistics and analytics. Your data has been pre-cleaned, or you've set it up in a way that you have a fairly clean, homogeneous source of data, fits on one machine, and it's something we manipulate in core. Models, the output are intended for human consumption, pictures, reports, maybe a list of coefficients that someone could go implement in a model, but the output is fundamentally for humans. And it's something we build infrequently. We build it offline, by hand, in an environment like SAS or R. This is the classical world. And this is my classical view of the pipeline, of what is done. We load up the data, maybe sampling it from a data source. We build a model. We evaluate the model and tune it. And then we publish the model. We put out the pictures, the statistics, the report, the coefficients. And we're done, and then we start again from scratch next month. So this worked really well, I think, and it actually, we were able to process increasingly large data sets thanks to Moore's law. Disks getting cheaper, processors getting faster. It was going quite nicely until the internet and mobile happened, right? So suddenly the rate of data growth that was available to you, that you could sample, jumped well past what Moore's law could keep up with. What data wasn't doubling every year, it was growing by factors of hundreds or 1,000. And both the internet and mobile did that to us. The internet let our businesses potentially talk to all the customers in the world, not just in our city. And the mobile, of course, opened up an entire new universe of sensor data at the personal level. Suddenly we're not starved for data at all, we're overwhelmed by it. And this is why companies like Google couldn't simply buy bigger and bigger machines, even if they had the money. They had to figure out ways to parallelize these operations and this analysis over thousands of machines. And that has changed things. That's changed the way we have to think about processing data, writing algorithms, and how we think about collecting data as well. So now the world looks a little different in the context of big data. Our data set is huge. We can actually have as much data as we like. And once we're done consuming all that data, there would still be oceans more of it if we wanted it. The data is noisy. It's diverse. It's not just from one source. And we have to process it in parallel. We can't possibly fit it on one machine. The output is typically more continuous. I am more often learning in real time in response to streams of data rather than offline, building a model once a month. Now I'm updating my model continuously as I see new data. So the whole process is online. It's very much an online affair, a real-time affair, not offline. And the output is intended mostly for machine consumption. I don't want a model that a human operator is going to look at or an analyst will look at to plan next month's purchasing. I want my purchasing systems to consume this information in real time as fast as it can to make even more optimal decisions. So this is a different world. And the pipeline ends up looking a little bit different too. At the core, this pipeline, which is kind of what we do inside the question mark in my earlier diagram, still has some common elements. We have to build a model, evaluate and publish it, but suddenly the input becomes harder. We have to get all the data in one place. We have to clean it, make sense of it, marshal it into some kind of distributed file system. And on the other side, deployment becomes a much bigger problem. It's not that I want to just output a model, a description, or a set of coefficients. I want to push something that I can consume in real time. I want a server, not a file. I want an API to query and not just a set of coefficients. So at the ends, things have gotten harder. And I think that unfortunately the classical tools, or even some more modern tools out there, aren't quite giving us answers to those new problems at the ends. For example, R is a fantastic statistics and analysis environment. I suppose the biggest problem is it's built for the classical world. It does the model building and model evaluation quite well. It does the evaluation and publishing quite well. Doesn't really necessarily help you with the building at scale, right? Because it's basically an in-core, one machine kind of environment. Doesn't really have anything to do with loading up the data or deploying your model to production in a way that you could query it either. It's the offline tool in the middle, and it's not really helping us solve the problems at the ends. So unfortunately, good old tools like R still have their place, but they're not going to be the whole solution to the data science problems in the foundation of the data science systems of next year and the next. Same with things, libraries like sklearn, fantastic library in Python. Again, has a better story perhaps for deploying your model to production. Since it's Python, it's embeddable into a lot of runtime production systems. And being Python, it's good at helping you munge data, process text, and so on, but still not necessarily helping you build a model at large scale in parallel across a bunch of machines. It's still an in-core sort of library. So better, but still a classical tool, a classical library that maybe isn't a complete solution to the problems we're facing now. Even something like Apache Mahout, which is a project I've contributed to a lot over the years, which does a better job maybe of the model building at scale since it's already Hadoop based, but still doesn't really help us deploy models. It's again a library. It's not a runtime system. It's not giving us an API to query once we've built the model that I can integrate into my production system. And it's not really maybe helping us grab data from a bunch of sources. So part of the solution maybe, but not the complete solution. So what are we going to do to bridge the gap in 2014, looking forward here? I would say that this is my one slide on what a complete solution probably does look like. Some elements of the kind of data science systems and servers we're going to have next year and on to really solve these problems repeatably, to mass produce, to push this into the factory. Number one, I think we're going to find that the sheer data volume is going to be not so much a hindrance anymore as almost a help. Large-scale data helps machine learning algorithms work better, and at scale, noise gets drowned out. So a lot of data analysis and machine learning algorithms and work spend a lot of time trying to solve the problem of what do I do when my sample's small? What do I do when it's noisy? At scale, you can almost ignore these problems, and that's nice. So we can focus on algorithms that do well at parallelization and don't have to concern ourselves so much with things like overfitting and noise. I think one way or the other, we're going to find systems that are going to have to leverage Hadoop or similar, but probably Hadoop. Hadoop's a mature platform now. You've got a lot of different execution environments, not just MapReduce, but Spark, for example. And we're going to need to build models at scale, and we're probably going to need something like Hadoop, a distributed file system and distributed processing environment to do the model building, at least. I think we're going to find that the industry converges or starts to focus a bit more on a couple algorithms that are friendly to large-scale learning. So the attributes of large-scale algorithms, they don't necessarily need to have a great story for overfitting, necessarily. They do need to be parallelizable, right? They need to be algorithms that easily split up over several machines, both for model building and model serving. And they need to generalize to diverse input. So I need algorithms that can handle lots of different types of input and do pretty well on them. I don't need specialist algorithms. There's actually just a handful of algorithms out there that fit this description. And I think we'll see tools and research focus on those. Things like random decision forests for classification or matrix factorization for recommendation. We'll see a tool and a research focus on these sorts of things. Lastly, I think we'll see infrastructure try to solve the deployment problem. So not just give us a model, built at data at scale, but have a story for serving that model, exposing an API over the model, answering questions from the model in real time, maybe even updating the model approximately in real time, and also having some story for automatically tuning, evaluating, and continuously rebuilding the model in the background. So very much a continuous system, one that more like we're used to when in the world of databases, right, where we have a a database is a continuous live system that you can query at any time. We're going to see that sort of paradigm arise in the data science tools world in a way we haven't yet to date with existing tools. So I want to wrap up the short sort of comments with maybe some do's and don'ts. So I realize that for a lot of customers or people, big data, whatever that means, is still a little bit new. But even if you're not ready to jump to the next step, which is the analysis and mining and extracting of value from that data, I think there's a lot you can be doing now in the next year to prepare for that. Number one, build your big data warehouse. I mean, if you're thinking about doing it, if you're not sure why you might collect this data, I would say just go do it. It used to be expensive, and you had to have a really good reason to store a bunch of data. Now it's not expensive, and now it's not hard. So there's really not an excuse to not be storing and warehousing data that might be valuable to you in the next couple of years. Do it now. I don't even think you have to worry about data format or quality. One of the premises of Hadoop is it's a schema on read system. So raw data is what we store, and we kind of make sense of it when we read it. So that means we have flexibility in the future. You have some raw data. You may think you want to parse it and read it in a certain schema today and a different schema tomorrow. That's fine. In Hadoop, this is the natural order of things. It gives you that flexibility. Wouldn't even worry about quality yet. Like, that's again something that, as I say, gets drowned out at scale, and we can fix later anyway. So just get the data in. It's cheap anyway. I think that we should also not worry about collecting too much data. Again, it's cheap, it's easy, and you never know what's going to be useful. It may not be clear why, for example, your server logs are from some obscure secondary system are of any use. But since it's so cheap to store them, why not? Let's store them now. And who knows what project you're going to do next year to analyze the performance of that system. Maybe it helps predict the performance of some other parts of your systems. Just store it now if it could be of any use. The problem with waiting, and you shouldn't wait, is that once you decide you do want to use a particular type of data, you can't retroactively go back and collect it for 2 years or 5 years. If you haven't started collecting now, you won't have it for later. So that's one of the key problems I do see if people deploying data science projects now. Now they've decided to collect customer data. Now they've decided to collect weather information, whatever it may be for your business. And unfortunately, that doesn't give them much to learn on. So they have to wait. They have to wait and collect and build until they can launch it. So think about that. And lastly, invest in your data science capability. I mean, today, as I say, data scientists are kind of this rare hybrid of engineer and statistician. But you can grow them internally. You can grow into data science, I think especially if you're an engineer. It's an easy path. Whether you do it by reading a book or going to training or just getting your hands dirty with tools, do it now. It will be useful in some way to have this capability within your organization. Even if you don't specialize, just having the basic knowledge of what it means and the tools at hand is definitely going to pay dividends in the next couple of years. Finally, I wouldn't be afraid to invest in proof of concepts. It's okay to get your feet wet. It's okay to try out a project, a data analysis project on a small scale. What do you have to lose, right? It's not as hard as it used to be. Could add a lot of value. There's easy ways to evaluate whether the results are quality or not before you even get near production. There's just not a lot to lose, and it's okay to start with small steps to prove the value to justify larger steps here. That's all I've got. Thank you very much. Appreciate it.